Hey everyone, let's take a look at another example, and this one's going to be a little more complicated, have a little more meat and potatoes to it. So we want to take it kind of slowly, so we're going to do it in little parts, probably multiple videos here. Alright, so I've got another beam. There's a pin support here at what I've designated as point B, and a roller support at point D. At the far left of the beam, there's a 200-pound force, that's at point A. And at the far right of the beam, there's a 300-pound force at point E. Then I've got this force distribution. It's a triangular force distribution, and it goes from C at 6 feet to D at 9 feet. There's 0 pounds per foot at the far left of this distribution, and there's 100 pounds per foot at the far right of that distribution. And we're kind of interested now in what's going to be the forces acting on this beam, and then what are the internal forces. But again, in order to find the forces, we first have to figure out what are the forces acting on the beam. So we do a sum of the forces in the x and the y direction based on this free body diagram. All right, so you can see I have a 200-pound force at the far left. There's a pin support here at B, so there's a B sub x and a B sub y. There's the roller support at point D. There's another force here, and that's the culmination of the forces here with this triangular distribution. We'll come back to that. And then there's a 300-pound force here at point E. All right, so let's go on to this triangular distribution. So I've got it redrawn over here. The far left-hand side of the triangle is 0 pounds. The far right-hand side of the triangle is 100 pounds per foot. This is at 6 feet, this is at 9 feet, so there's 3 foot separation in here. So the idea here now is we have to look at the centroid of this distribution. And we know, you can look at the back of your book or previous videos, the centroid of a triangle is 1/3 of the way from the base. Now the base of this triangle is actually this side, okay? Because I'm interested in where this distribution has its centroid, not in this direction. So the centroid is going to be over here, right? And it's going to be 1 foot, because it's 1/3 of the entire base, so 1/3 of 3 feet. 1/3 of the way from the far right-hand side, so that's 2 feet from the far left-hand side. And so this is going to be at 8 feet. Okay, so that distribution is going to be at 8 feet. Right there. Then what is the value of that distribution? Well, I've got a triangle, so it's 1/2 base times height. So 1/2, the base is 3 feet, and the height is 100 pounds per foot. And so that's going to be 150 pounds, right? The feet cancel out. 1/2 of 100 is 50. 50 times 3 is 150. So there's a force then right here. I can consider the force, as I'm looking at the entire beam, the force to do this distribution is 150 pounds, all concentrated at 8 feet. All right, so there's my forces acting on this beam. So now I do the sum of the forces in the x, sum of the forces in the y, and the sum of the moments. Some of the forces in the x, there's only bx, and that's going to sum out to 0, so I'm just going to get rid of that. There's really no force in the x direction. Then as I look at the sum of the forces in the y, I've got sum of the forces in the y. I have negative 200 pounds plus b sub y minus 150 pounds plus D minus 300 pounds. And that's all going to equal 0, right? And so I'm going to get BY plus D. Those are over here. And then I got 200, 350, 650 pounds. So I have two unknowns. And so now I can do the sum of the moments. And I'm going to choose the sum of the moments around B. That way there's B is out of the equation. Okay, so I'm going to do the sum of the moments around B. And I'm going to get 200 pounds right? 200 pounds is trying to rotate it counterclockwise. So 200 pounds times 3 feet, and that's going to be positive. And then nothing at B, because the distance is 0. Then I have 150 pounds, and that's going to try to rotate it clockwise. So negative 150 pounds. And that's going to be 2 feet away from point B. Nope, that's 5 feet. Excuse me, that's 5 feet. Oh, and I forgot. Nope, that's right. That's 5 feet. And then there's D, which I don't know what D is, but D is trying to rotate it around B in the counterclockwise direction. So that's going to be plus D, and that's 6 feet away. And then finally, the 300-pound force is trying to rotate it around point B. It's going to try to rotate it clockwise. So minus 300 pounds. And that's going to be times 12 feet. And so I can solve this for D. Let's see, let's do this real quick. I'm going to have 750 here and 3,600 there. Those are negative. So 750, 3,600. So that's 4,350. Those are negative, so it's going to go to the other side. So I'm going to have D times 6 feet equals, those are negative, they're going to become positive, so it's going to be 4,350 foot-pounds. And then 200 times 3 is 600, but that's going to be negative, so minus 600 foot-pounds. Or pound-feet, whichever you want to use, is fine with me. And so 4,350 minus 600, that's going to be 30, what is that, 3750 foot-pounds. And so D is equal to 3750 foot-pounds divided by 6 feet. And then we solve that out for D. I'll let you do the math on that. I'm not going to do that right now. Actually, I guess I can. So that's going to go in 6 times, brings a 1 over, going to go into that twice, brings a 3 over, and there's a 5. So 625, the feet cancel out, pounds. So D is 625 pounds. And then remember the sum of that is 650. And so BY is not very big. B sub y is equal to 25 pounds. All right, so I've solved for the external forces, the support forces acting on this beam. Okay, so that's all solved. All right, in the next video, we'll take a look at finding the internal forces and moments as we go across the beam. And we're going to do it in arbitrary locations, but we'll have to set that up. All right, so far, any questions, put them in the comments below.